Okay, picking up with where we left off from the last video, let's introduce some new trigonometric identities. These are known as the sum and difference identities, and for all three of our main trig functions, sine, cosine, and tangent, we can essentially rewrite sine, cosine, or tangent of the sum of two angles or the difference of two angles with a somewhat more complicated expression, but you'll see the benefit for that here in just a moment. Now, before we begin, I would like to point out that while our textbook writes each of these as two separate trig functions, you may find online these written in a single form. So again, I've seen some textbooks write them this way in a single compact form. So cosine of alpha plus or minus beta might be written as cosine alpha times cosine beta minus plus sine alpha sine beta. So if you look closely and read this literally, cosine of alpha plus beta would require this expression with the minus sign, because over here the plus sign was on top, so the minus sign is on top here. And cosine of alpha minus beta would require us to use the bottom form of the expression over here. And you can see how that correlates to this expression. Cosine of alpha plus beta equals cosine alpha beta minus sine alpha sine beta, and vice versa down below. And it is worth noting that alpha and beta are used here as Greek letters to represent unknown angle measures. We're doing this because, well, we're in the habit of using theta, another Greek letter, to represent angle measures. But I don't want to use theta twice because that would imply that theta is the same in both cases, where in this particular series of identities, these two angles must be different. These two angle measures must be different from one another. So we're using two different letters. Not only might you see these identities written this way, combined into one, but I've also seen them written with the letters A and B. So you might see cosine of A plus or minus B equals cosine A times cosine B minus plus sine A times sine B. So be on the lookout for that when researching and practicing on your own. The same can be done for these other two examples on the right side as well. And here are those two other formats. I would really recommend pausing the video at this point and looking through how each of these trig identities are written. Pay close attention to how the sines and the cosines are grouped in each case. For this example, cosine goes with cosine. In this example, it's sine with cosine, and then cosine with sine. And in this bottom example, we've got the sums of two tangents, then the differences of two tangents, then one minus and one plus. It's kind of interesting. There are definitely patterns in these identities, and before you can start to memorize them, I think it would be helpful to notice those patterns. Now, as far as us using this, let's talk about the following here. So you're being asked to find exact values of the following expressions, and this would be done without a calculator. Certainly we can type cosine of 165 into the calculator and get a decimal result, but perhaps you'd like to find the exact and precise result. Well, 165 degrees does not land nicely inside the unit circle that we memorized. In fact, it's the last 15-degree position before 180. And in the circle that we memorized, we knew the last 30-degree position before the 180-degree mark. So let's think about this for a second. Cosine of 165, if I need the precise answer, well, it might be helpful to rewrite this as cosine of 120 degrees plus 45 degrees. And the reason for that is because using the unit circle, I know what cosine and sine of 120 degrees is, and I know what sine and cosine exactly is for 45 degrees. And the sum of those two add to 165, so therefore we can use a sum identity for cosine. Now the sum identity for cosine was this top one up here. If I have cosine of two angle measures that are being added together, then it would result in this format. So I'm going to use this format to rewrite the expression down below. And if we considered 120 to be our A or alpha value and 45 to be our B or beta value, then cosine of 120 plus 45 is cosine of 120 times cosine of 45 minus, we're using the minus sign here because that's how our sum identity worked for cosine, minus sine of alpha times sine of beta. And from here on out, we would just evaluate using the known values from our unit circle. So the x value at 120 degrees is negative 1/2. The x value at 45 degrees is radical 2 over 2. And the y value at 120 degrees is radical 3 over 2, and the y value at 45 degrees is radical 2 over 2. And for each of these results, I'm just mentally considering the unit circle. 120 degrees was this first vertical position, or first position past vertical on the unit circle. 45 degrees was this position halfway in between in that first quadrant. So mentally, I was able to compute those very quickly. As far as multiplication goes, no need for common denominators. We multiply numerators by numerators, denominators by denominators. So I'm left with negative square root 2 over 4 minus square root 6 over 4. And we do have a common denominator here. So I'll say something like this, that the result is negative square root 2 minus square root 6 divided by 4. And we now know the exact answer for cosine of 165 degrees. And if you're not sure of your result, an easy way to check is to type both of these into a calculator and see what you get. Now I've done that with my TI Inspire, and my calculator is set to degree mode right now because 165 is a degree measure, and cosine of 165 is negative 0.9659, and the opposite of square root 2 minus square root 6 is also negative 0.9659. So I'm pretty satisfied that we've done a fine job there. For number 16, we can do much the same work here. I'm going to consider 105 as 60 plus 45 because, again, these two angle measures are well known inside of our unit circle. Now, using the sum identity for sine, and we've got sine of alpha times cosine beta plus cosine alpha times sine beta. And that's the way our sum identity works. And after we use the unit circle to evaluate each of these four expressions, we see the following. And we can further simplify this way as well. And it is worth noting that while I used 60 plus 45 to equal 105, you could have also done something like 135 minus 30. And since those are two angle measures that are known within the unit circle, we could have used a difference formula for sine as well. And ultimately, you would have ended up with the same result. Now this page is getting pretty tight, but hopefully you get the idea with the sum and difference of sine and cosine. Tangent is done much the same way. Just be a little bit more careful with tangent because of the fractions that are involved. Now here's a completed copy of the notes from prior semesters, so you may want to take a look at it. And if you need to pause the video to try this on your own and compare your notes, now would be the time to do so. And while we're here, I'll just go ahead and talk a little bit about the sum and difference rules using radian measures as well. This is where some students tend to have a bit of difficulty. Just remember that the rules follow or the rules operate the exact same way, whether our angles are measured in radians or degrees. What's tricky here is finding a pair of known angle measures that add or subtract to, in this case, pi over 12. And so what I like to do is I like to find um, just different multiples of 12 that will add or subtract, in this case, to equal 1. And so I thought to myself, well, 4 pi over 12 minus 3 pi over 12 equals 1 pi over 12. And if we consider the fractions that are created here, well, these fractions will reduce to 1/3 and 1/4 respectively. And now that we've identified angle measures that fit nicely into the unit circle, then we'll go ahead and operate with the sum and difference rule as we've done in the past. For this case, the difference of the difference identity for sine requires sine of pi over 3 times cosine of pi over 4 minus cosine of pi over 3 times sine of pi over 4. Each of those components can be evaluated and further simplified, and we again now have a precise result. The last example in this row, cosine of 7 pi over 12, can be done the same way. In this case, I chose 3 pi over 12 plus 4 pi over 12, which would be pi over 4 and pi over 3, respectively. And utilizing the sum identity for cosine would simplify as follows. For the final examples of this video, they may look intimidating at first, but they're actually quite simple. What we need to do here is recognize which of the trig identities does this pattern fall into. Well, we've got sine of some angle times cosine of a different angle plus cosine of the first angle times sine of the second angle. And if I look through my sum and difference identities, it looks to me like we're operating with the sum identity for sine. We've got sine of alpha times cosine beta plus cosine alpha sine beta. So if this is the sum identity for sine, then what we're really saying here is that we've got sine of 20 plus 10, which is quite simply sine of 30, and we know that the y value at 30 degrees is equal to 1/2. So this whole expression up here is really just equal to 1/2. In example 25, I've got cosine cosine minus sine sine, and the identity that uses cosine cosine minus sine sine is the sum identity for cosine. So really what we're looking at here is cosine of 70 plus 20, which is just cosine of 90 degrees, and we know the x value at 90 degrees is equal to 0. For example, number 27 here, I'm looking at tangent plus tangent in the numerator and 1 minus tangent times tangent in the denominator. So again, looking at my grouping here, when the tangents are summed and we've got 1 minus the product of the tangents in the denominator, we're looking at the sum rule or sum identity for tangent. In number 29, we have sine times cosine minus cosine times sine, and that's an indicator of the subtraction identity or difference identity for sine. And sine of negative 6 pi over 12 would be the same as sine of negative pi over 2, which is this position down here in our unit circle. It's the clockwise rotation from the positive x-axis. And the y value at this particular angle is -1. And lastly, cosine times cosine plus sine times sine is an indicator of the difference identity for cosine. So we have cosine of pi over 12 minus 5 pi over 12, which is cosine of -4 pi over 12 And 4 over 12 reduces to 1/3. So we're talking about cosine of negative pi over 3. Now that position is down here. The last vertical position, or last position before vertical in a clockwise rotation, and the x value of that position is 1/2. And if you wanted to check your work by entering this expression into a TI calculator, we end up with this result here. I know that's right on the edge of your screen, but I have switched to radian mode in the calculator, evaluated each of these expressions, and the sum does come out to be 1/2. So I would say that's pretty nice, being able to evaluate such a complicated looking expression here without the use of a calculator by just knowing some nice trig identities makes this quite helpful and useful for future work. Thanks for watching.